Hello, and in this video we'll be looking at section 5.4. We're going to introduce what a logarithmic function is. We're going to start with the question we're going to look at exponential functions here. Is the function f of x equal 2 to the x power 1 to 1? So if you look at that, we would do that with the horizontal line test. We would look for horizontal lines crossing through this graph. As you can see here, horizontal lines would only cross the graph once, so it is 1 to 1. We don't have any horizontal line crossings of more than one time. Does it have an inverse? We would have to say yes to that as well, because it passes the horizontal line test and is 1 to 1. So if we take a few points here and we try to graph the inverse, that just means we're going to switch the x and the y value. Start with this value right here. That's 0, 1. So that value of 0, 1 would be graphed at 1, 0, which is right here. So we'd start with that graphing point. We'd switch the value of that from x to y. So that's 0, 1, and that would change to 1, 0. We go along this graph, we have another point here at 1, 2. So this point 1, 2 would change to 2, 1. So it'd go to this point here, 2, 1. Inverse is swap the x and the y value. Then we have another point up here, 2, 4. 2, 4 would swap to 4, 2. So it would go to 4, 2. And then if we have some other points here, this looks like negative 1, 0.5. So negative 1.5 would be a point. So that means we'd go out 0.5 and then negative 1 would be right here. 0.5 and negative 1 would be that point. And we have an asymptote here, it looks like, so we're going to have an asymptote here. So that means this is going to come close to this line, and we're going to come up through these points to get the graph of the inverse. And the graph of the inverse is going to be what we call a logarithmic function. This is going to be y equals log with little base 2, because that's the base we have here, of the value x, just like this was x. So this is going to be the equation log base 2 of x. So this is the inverse of 2 to the x. So we started off with the graph y equals 2 to the x. If we want to make the inverse of this, we swap the x and the y value, so we get x equals 2 to the y value. So that's the inverse. But we don't write it that way. We have to, in order for us to solve for y, we have to rewrite it in a different form. So that becomes the log base 2 of x. So rewriting this in this form allows us to write y equals. There's no simple way to solve this for y, so we have to have a way to rewrite it. Now this will work generally for any base down here. So in any general base, we can call it log base a. The function is log base a is the inverse of the function a to the x. Instead of 2 as we did previously, now we can use any base a. And we can write the inverse as log base a of x. That's how it's said right here. So that's the inverse function of a to the x. So we can use any base now. 3 to the x is log base 3 of x. 10 to the x is log base 10 to the x. We'll have a special way to write that. We're going to only work with logarithms with bases greater than 1. And we're going to note that these are logarithmic growth functions. So they're growing as we go from left to right. in the picture, growing from left to right. Okay, so let's look at some properties of a to the x. So some properties. So actually we're going to look at the properties of log base a to the x. So we're going to look at some of these properties here of this function. So some properties of this function. Domain. So the domain here, since we have a vertical asymptote, there, the domain is going to be from 0 to infinity. From 0 to infinity, it starts here and goes this way. That's our domain of the log base a of x. Our range, it's going to go from up all the way up, so the range is going to be from negative infinity to positive infinity. Our x-intercept, is the inverse of the y-intercept, and the y-intercept of a to the x is 1 or 0, 1. So the x-intercept is going to be 1, 0. Y-intercept. Since we have an asymptote at the axis here, we're going to have no y-intercept for this logarithmic function. And then we need to look at any kind of bounds. So we have a boundary here, but as we go to the right, as the function bounds out to the right, so as x goes to infinity, we have a boundary. The function f of x is going to go to infinity. It's going to go rise as we go to the right. We don't really have a boundary going left because we have an asymptote. So at the asymptote, we have a boundary, but we don't have a left bound here. We only have a right bound on the function. At the asymptote, as x approaches 0 from the positive side, f of x approaches negative infinity. It goes down as we approach from the right hand side. We go down. So that's going to be, at the asymptote, this is going to be its boundary. So we have a right bound going out to the right. It's going up as we go to the right, so it's going to go to infinity. As we go left, it's going to go to negative infinity. As it goes to 0 anyway. It can't go all the way to the left. We have an asymptote there. Alright, so those are the properties. It's the definition of a logarithm. And this is how we write it if we are writing it in logarithmic form, which happens to be the inverse. So that's the big key here, is that the log is the inverse of an exponential function. It's the inverse of the exponential function with the same base. Alright, if you have any questions about that, we're going to continue on writing things in logarithmic form for the next video. You're going to need to know some properties of those logs, and we're going to continue on with that.